Hello everyone, this is the preview lecture for lecture 12. In lecture 11, the previous one, we have studied the concept of subband. And today we wanted to calculate the electron density by using the Schradinger-Poisson equation. But not in fully consistent way, but inconsistent way. In the previous lecture, we have calculated the total number of electrons. So we did calculate it. And from that calculation, we can calculate the N total and divide it by Lx and Ly. That gives us certain quantity per unit area. So the electron is uniformly distributed over our thin plate. But the question is, although we understand the dependence on X and Y, which is uniform, but we have no idea up to now the dependence of electron density on the G-directional variable. So the depth dependence is not known to us. So in order to calculate the G dependence in our case, actually we have to consider the wave function. Up to now, we have thought about just eigenenergies in order to calculate the occupancy of each energy state, and summing them all, we had the total number of electrons. But depending on the shape of a wave function, actually each square, we can have a different distribution. Each state specified by kx, x-directional momentum, and ky, y-directional momentum, and n, z-directional quantum number contribute this quantity. Actually, the square of the wave function gives some information about spatial distribution of our electron. Recall that the wave function can be written as this form. So here the wave function is given by plane wave along x direction and plane wave along y direction and confined wave function along z direction. Of course, we have a certain coefficient, the normalization constant. In order to interpret the square of a wave function as the probability density function of electron, then we have to have a certain normalization condition. So, square of our wave function, which is integrated over whole space, should be unity. So that is required condition for our interpretation of the PDF function. So how can we satisfy this one? First thing we will do is just to apply the G-directional normalization condition. So we say that the G-directional wave function, its square integration gives us still number 1. Then it simply means that now our condition becomes Lx times Ly and A square should be 1. Since Lx and Ly are given numbers, we can immediately find that. Okay, so our normalization constant is simply given by this form. Therefore, each state contribute like this. Here, this is corresponding to square of A, and this is corresponding to the square of G-directional wave function. And it is noted that for different n values, our wave function will be differ. Then the contribution to the electron density will be different for different subbands. So if we apply the previous discussion to our one-dimensional infinite potential well problem, then now we can say this is the G-directional wave function. The first condition is this G-directional wave function should be normalized to number 1. So we can easily find that the value of leading coefficient A sub z is this number regardless the value of n. So when fully occupied, a state in the nth subband contributes an electron density like this. Here 2 over L sub z comes from G-directional wave function. Also we have 1 over Lx and Ly, which is related with the x direction and y direction. And finally here we have square of sine function, and this is corresponding to the G-directional wave function. As I told you before, if we have different n values, for example 1 and 2, then our sine square of pi lgz and squared sine of 2 pi over lgz will look quite different. So depending on the subband index, we will have quite much different electron distribution. So let's go to the MATLAB example. So this slide just shows the preparing some constant. So this is repeated once again, and we will consider certain number of electron subbands. Here we have used 10 subbands. After that, we wanted to calculate it. So just to run a loop over the subband index from the first subband to 10th subband, and we just calculate the energy level, and from this energy level we can calculate the subband number and total number. We have done it already. However, one thing we have introduced in this lecture is the elect. This is corresponding to electron density, and this electron density is defined as nz times 1 vector. So this is just a vector, and depending on the position, see here we have a G-directional position, and we have made square of sine. Yes, so we have made it. So this is the way for us to calculate electron density. Please note that this elect, the variable called elect, is not a scalar. It is a vector, and we can plot this vector as a function of position, and this is given here. This is the electron density we have calculated. Oh, here we have a boundary and another boundary. So at these boundaries, due to the assumption of infinite potential well, wave function itself vanishes. Also wave function itself vanishes. So its square is also 0. We have no electron density at all at those points. Okay, and we have the most highest electron density near the center. So up to now, we have applied our discussion about electron density to infinite potential well. However, you know that in our realistic case, we have different potential barrier. The shape of potential well is not flat at all, so we have to consider more realistic potential energy. Then how can you do that? So since we know only the electrostatic potential, first of all, we have to reconstruct the conduction band minimum values out of this electrostatic potential phi. But we have done it before, because when we multiply minus q to electrostatic potential phi, then what is the physical meaning of this quantity from our convention? In this case, minus q times phi is given as just position, energetic position of intrinsic Fermi level. And you know that the energetic difference between the conduction band minimum and intrinsic Fermi level is given as a constant in our discussion. So therefore, we can say that the conduction band minimum, here written as B, can be simply written as minus q phi plus EC minus EI. Once again, this is a given constant, so only electrostatic potential determines the conduction band minimum. So that conduction band minimum is used as the potential energy in the Schradinger equation. So then our Schradinger equation just looks like this. Yeah, here we have a G-directional Schradinger equation, and previously we have not considered this potential term because we have considered just infinite potential well problem, which has a flat potential inside the infinite potential well. However, now we can have a general potential, which once again is given by minus q phi plus certain constants between the certain constants corresponding the energy difference of conduction band and intrinsic Fermi level. Okay, so this is the equation, and here we have discretization. So as you can see here, we have second differential operator. Second differential operator can be easily mapped into this form. Of course, it has here square of delta G. However, that can be multiplied to the left hand side and right hand side. So that's the reason why our second order differential operator is combined with here square of delta G and square of delta G. As you can see, these terms are just given term which is not related with derivation. And let me show you the simulation flow. So anyway, in order to solve the Schradinger equation, we need initial potential. So the initial potential can be obtained from the semi-classical simulation. In our case, it means that nonlinear Poisson equation. So first, solve the nonlinear Poisson equation. Then you will have the potential. Although that potential is not fully consistent with the Schradinger equation, but it's okay. It is a good initial guess for our electrostatic potential. Then, based upon that electrostatic potential, although not perfect, but by using that electrostatic potential, solve the Schradinger equation. When you solve the Schradinger equation, you will get the wave function and eigenenergy. And from these two information, you can calculate the electron density as we have studied just before. So by using this electron density, later we will feed this electron density to the Poisson equation again, and that will give us another loop, self-consistent loop, to calculate the electrostatic potential and electron density consistently. So that is our eventual goal, but for a while, just to concentrate this one directional simulation flow. So now already you have nonlinear Poisson equation, and our goal is just to calculate the Schradinger equation, and from that information calculate the electron density as a function of position. Okay, so as I told you before, normalization condition of our G-directional wave function is simply given by this G-directional wave function itself should be normalized to number 1. Square of G-directional wave function, when it is integrated over the entire G space, then we should have unity. And its discretized version is shown here. So since we have assumed that uniform spacing along G direction, actually this dz can be easily approximated as spacing. But here we have one caution: be careful for the interface nodes. So interface node, let's say that this is corresponding to the interface and this is corresponding to interface. If you are trying to numerically integrate it, then point is for this bulk node, then now you have a full delta G, and here you have a full delta G. However, for this top interface node or this bottom interface node, what you have is just half of delta G and also half of delta G instead of full delta G. You can easily understand this one, but fortunately in our boundary condition, we have assumed that the wave function at these two interface nodes vanish. So, so we can just neglect that contribution. But anyhow, in general, when you make integration, numerical integration over G direction, please be careful for the interface nodes because they have just half control volume than the other bulk nodes. Okay. So finally, since we are talking about the silicon conduction band, silicon's conduction band, now we have to think about 6 different valleys inside the silicon. So as I told you before several times, so silicon, it has 6 different valleys and they can be categorized into 3 different valley pairs. So there are 3 pairs, so in total we have 6 valleys. So here we have a valley whose x-directional mass is typically large and y-directional one is typically large and g-directional is typically large. If we consider the confinement along the G direction, then you can easily understand this one. This valley whose D-directional effective mass is heavy, that will give you the lowest energy. And other ones corresponding to light mass, then they will give higher energies and contribution to the total electron density will be relatively small. Okay, so now you have homework number 12. The due is next Monday, and it is based upon your homework number 8. What was homework number 8? That was the nonlinear Poisson equation solver, semi-classical nonlinear Poisson equation solver for a double gate structure. And consider the gate voltages from 0 volt to 1 volt. Consider 0.1 volt spacing. For each gate voltage, first solve the nonlinear Poisson equation. You don't have to do additional effort. It has been already done in your homework number 8. Then taking this electrostatic potential and treat it as a just given number. Then calculate the electron density by using the Schradinger equation. Of course, you must consider 6 different values. So it means that you have to solve Schradinger equation at least 2 times. Why do we have to solve it 2 times? So depending on its mg value. First solve the case for mg equal to 0.91 rest mass. After that, solve another case where the mass is much smaller than 0.91, 0.19. So then by collecting all contributions from these 6 values, please calculate the electron density. Here electron density is not the integrated one, but the electron density as a function of position. And for each gate voltage Vz equal to, for example, 0.5, then please draw the semi-classical electron density and quantum mechanical electron density. You will find very interesting difference from this comparison. Okay, so see you soon. Bye.